Hey, how's it going? It is Christmas Day 2020. We're almost through this horrible year. It's been horrible for a lot of people. Merry Christmas to everyone. I wanted to do this book review. It's my first book review I've ever done. It's for a book called High School Mathematics Challenge. It is written by Dr. Kanbir. I'm not sure I'm saying that name perfectly correctly, but that's probably pretty close. Anyhow, and also Richard Spence, who is a PhD candidate in computer science. They wrote this book together. It's, what is it for? It's for AMC 10 and 12 and MathCon Prep. MathCon is another competition in the US. It currently has over 200,000 people taking the contest every year. They claim on their website that they are the fastest growing math competition in the US. I don't know anything about their background statistics, but I will include a link to MathCon in the video description. What is this? It's 10 practice tests with solutions, and they're basically essentially mock tests. The thing you have to take in mind with mock tests is kind of the following. When the test makers for MAA make their competition, they have a huge wealth of resources to work from. So they've got all kinds of people doing, problem checking, and they have a committee, and all kinds of people work to put forth the best possible thing. Mock tests don't typically have that kind of resource advantage. So they do the best they can. I thought this was a pretty great book. It's printed by his company, which is MathTopia. Apparently, he's able to print his own, which is cool, MathTopia Press. I will include a link to it in the description as well. In addition, I've actually spoken to Dr. Kanbir a couple of times now by Zoom meetings, and this is just important to me. He seems like a nice guy, which is good, right? He's a good person. He loves math. He wants to help students. And so he created this book to be able to do that. It's going to be kind of a hybrid between all three of these. For example, in some of the tests, you will see in the answer space, let's see if I can find one in practice exam 1, something like in problem 22, where it will say none of the preceding. And that idea of none of the preceding answers is not really prevalent on AMC 10 and 12, but it is on MathCon. And so this is designed for all three in mind. It's going to use a lot of the same fundamental concepts that you need to prepare for the AMC 10. So when can this benefit you? Well, number one, if you've done all of the AMC 10s and maybe the 12s as well, and you're looking for more source material that you can use to study, this is a chance for you to, again, practice your skills. And so it's going to give you that opportunity as well. In addition, MathTopia is having a class that starts this January 10th. It is 10 sessions for $290. It will be held on the weekends. I will include a link to the description to the sign-up list for that class in the run-up to both MathCon, which is held I think on January 19th, and obviously the AMC series held in early February. And so that's going to run. Why am I mentioning that? Because I'm going to help teach it. Cool, right? Dr. Kanbir asked me, and I was honored to accept his invitation to help teach the class where we'll be going through this book specifically. And so you will need a copy of the book in order to take the class. I will include a link to where you can buy the book on Amazon in the video description down below as well. I plan on doing more book reviews in the future. Not all the time, but sometimes. Because you need to know about different resources that are available to you that you can use to improve your skills. And this is one of those resources. I found it quite enjoyable. There's a lot of really great problems in here. As I noted, there is going to be, it's not going to be the same exact approximate linear increase in difficulty that the AMC is going to have with all of their test solvers and committees and meetings and all of that. They get to really try to perfect their product. But this is going to give you an excellent chance to practice a lot of the fundamentals that are used not just on older tests, but on the modern tests as well. And one we're going to look at today, we're going to look at 4 problems in a moment, one of which is going to use the AMGM inequality. And so we're going to look at that. We'll be right back to see problem number 1. I've selected these 4 problems. I wanted to get you a feel for the style of problems that you'll be doing in the book after you pick up your copy. All right, be right back. Okay, so this is the first problem that I wanted to do. Again, I found the problems really enjoyable. Most of them. There's a couple that are like, I don't know, maybe it's not one that I personally enjoy. But a lot of them are really well designed. This was kind of a neat one. It came from Practice Exam 1. This is problem number 10. The number n equals a bunch of ones is formed by writing 105 ones in a row. What is the sum of the digits of the product 105 times n? Well, right away, you're probably thinking, oh, I mean, if I had to multiply, whatever, ending in a bunch of ones, times 105, oh my gosh, that's going to take a long time. That's a sign. That's like a note from the test makers. Don't do that. Don't make yourself suffer, right? If you were to try and do it this way, you'd probably take the rest of the test or something, trying to multiply it all out. So there's got to be some kind of a shortcut, right? That's like, they do that intentionally. They put a big roadblock in front of you so that you feel like, oh, that'll take forever. You're right. Then don't do it that way, right? So we're going to do it a different way. And, you can kind of just think about it. There's got to be something. I'm not going to change this in any meaningful way, but what about the 105? Can't we write that as, I don't know, a bunch of ones times 100 plus 5? Now, why would we want to do that? Well, because this is going to be all of those ones with 2 zeros at the end. Cool, right? So you would have all of these ones with 2 zeros at the end. And then when you do the 5 times all of those, it's going to be all of these replaced with 5s, and there's going to be 105 of them. So it's going to be 5, 5, 5, 5, 5, 5, 5. And then it wants to know the sum of the digits of this when I add it together. And okay, so the first 2, when you put 5s here, are not going to give you 6. All the rest of them will, though, right? But where's it going to stop? Well, because we only added 2 zeros to 105 ones, you're actually going to stop with the 5s 2 ones short. And so you would have 1, 1, 6, 6, 6, 6, and so on. And then down to, at the end, you would have a 6 followed by 2 5s. Well, again, these 2 5s and these 2 1s could be combined to make more 6s, which makes your life a lot easier. There's going to, in fact, be this number here was 105 of these with 2 more zeros. And then that means there's only going to be 103 6s here, plus 2 more 6s with the 5 and 1s combined. So in other words, all the actual 6s, there will only be 103 of those, because the other 2 are right here for the 1s in the original 105 1 expression. So then we're basically doing 6 times 105, which is C, 630. On to the next one. All right, so this is going to be Practice Exam 5, problem number 5. Again, all of this from the book High School Mathematics Challenge. This is really a brilliantly designed problem. You kind of feel like you have the answer, and then if you're not careful, they're going to trap you into picking the wrong one, just like the real test. I really enjoyed this one. Whoever wrote it, very well done. How many integers x are solutions to the equation this expression equals 1? Well, we have some options, right? We could split this up because it would be this product to the x times this product, right? Because of the x plus 1, you could make it, right? If I have a to the x plus 1, that could be equal to a to the x times a to the 1. But after looking at that in my mind, don't like how it looks. I mean, what are you going to do? Divide by the a underneath the 1 and you would have 1 over a non-factorable expression? I think I'll pass. I think that's probably not the right plan. So the next thing that we would say is, well, how about looking at the 1? How are you going to get 1? And most people are going to think of the first two ways. Case 1, x squared minus 3x plus 1 would need to equal 1. Okay, so we would need to know when does it equal 1. And then also case 2, the x plus 1 could equal 0. The reason that would work is something to the 0 power would equal 1, but there's actually another case. And the last case is case 3, where x squared minus 3x plus 1 is equal to negative 1, and x plus 1 is even. So if x plus 1 is an even number and you have negative 1 inside, of course that too will become positive 1. So let's do this one here first. If this expression inside is 1, 1 to any power is 1. So you can just subtract 1 from both sides and you will get x times x minus 3 equals 0. This will give you x equals 0 and 3. If x plus 1 equals 0, that would mean x equals negative 1. Again, it doesn't really matter what happens inside when x is negative 1. You can plug it in if you want, but anything to the 0 power, actually I guess it does. We don't technically define 0 to the 0 in most cases. We don't know yet. There's some disagreement apparently. I read that in one of the AOPS books about whether that would be 1 or not. So maybe that argument hasn't been settled with super smart people above us who determine these kinds of things. So until then, just in case, I guess, negative 1 plus 4, it's not going to be 0. So because it's not 0, then this is going to be fine. It will equal 1 because it's to the 0 power. Okay, then what? Last one is, what if this is negative 1? Let's try this. If I move this negative 1 over, you will get x squared minus 3x plus 2 equals 0, which can be factored to x minus 2 and x minus 1. And again, if you're not careful, if you just go for 5, because you've got 2, 3, 4, 5 values for x, and we're looking for how many integers x, right, you could get 5. A very good trap answer. But they're not going to trap you, right? Because you're always checking to make sure that you didn't violate any other rules, such as x plus 1 is even. This is why I will write things like this on my paper while I'm solving sometimes, because I won't forget that way. So if I plug 2 into here, it's not going to come out to be even in the exponent, but 1 plugged in does, and you can see that 2 minus 3 is negative 1 to the second power, will produce 1. The answer is in fact 4. We're going to check out the next question. All right, continuing on with the book review of High School Mathematics Challenge. This one also came from Practice Exam 5. It was problem number 11. So this is another different problem type covering a different topic. In this case, we're going to be doing some counting, but if you do it correctly, you're also going to be doing some number theory. So I like those kind of hybrid, multiple concepts pulled into one problem. It's great and it's well placed in the test. So how many 3-element subsets of basically the integers from 1 to 12 are there whose sum is divisible by 3? Okay, so one example is 1, 2, and 9. First, you should know the divisibility rule for 3. I mean, if you've been doing competition math, this is something taught in Beast Academy. It's learned about 5th grade, 6th grade. You should have known it by now if you're watching a video like this. Hopefully you do. It's that the sum of the digits will be divisible by 3. So if I add this up and get 12, you already know 12 is divisible by 3, but you can also say 1 plus 2 is 3. Since that's divisible by 3, so will this number, this sum of these 3 numbers be divisible by 3. And so that's fundamental, of course, but I mention it anyway just in case that you don't know. So what else are we going to do? We really don't want to do trial and error with the numbers. Like that's a waste of time. Instead, what you want to focus on, and I've actually picked up a similar concept from a previous AMC. I don't remember which one it was specifically. Maybe you'll remember. It's probably happened multiple times. It's a very well thought of concept. And that's that if you're trying to add up a number of numbers, integers, and find that their sum is divisible by 3, well, then you can focus on their remainders when they're divided by 3. So of these 12 numbers, you will have exactly 4 that have a remainder of 1. You will have exactly 4 that have a remainder of 2, and exactly 4 that have a remainder of 0. So we can say that all of them are congruent to 1 mod 3, or congruent to 2 mod 3, or congruent to 0 mod 3. Again, I use this just so that if you're not used to it, you need to become more used to it so that you can be doing the number theory book in the future. And the more that you get these little icebreaker kind of situations, the sooner that will happen for you. It's going to be an essential topic. All this means is that we're dividing any number by 3. This is the remainder. It doesn't have to be the remainder. In fact, we can also say that 4 is congruent to 1 mod 3, and 1 would be congruent to 4 mod 3. So you can turn them back into larger ones. It's just basically saying that all such numbers have the same remainder. We don't use the congruent symbol that you use in geometry. It looks like an equal sign with toothpaste on top. We don't use that one. The toothpaste commercials, right? When they, yeah. I hope you don't put it, that's too much toothpaste. Anyways, yes, we use a triplicate equal sign, if you will, in number theory to indicate congruent. And so yeah, that's how that's going to work. So all of our numbers are going to be in these categories. That's all you can have when you divide by 3. And there's going to be 4 of these, 4 of these, and 4 of these. So we need to look at cases. Let's say I had a 1 involved. What could the other 2 numbers be? Well, here's the part of number theory that can benefit you. The sum of my remainders must be 0 mod 3, right? So if I have a remainder 1 and I combine it with a remainder 0, the other remainder is going to have to be 2, because the sum of these will need to be a multiple of 3 also. And so then one case, you would have, we'll call this case 4 actually. I want to look at case 1 would be if we had all remainder 1s. So if I had 1, 1, and 1 as my remainders. These are the remainders, keep in mind. Remainders. Then case 2 would be if I had all 2 remainders. So remainder 2s. Let's just look at an example so you can be convinced that this is actually true. What are 3 numbers with a remainder of 2? They don't have to be from 1 to 12, but we'll choose them from there anyway. We could do 2, 5, and 8. All of those have a remainder of 2 when you divide them by 3. And if you add them all up, you will get 15, which is divisible by 3. Okay, so that's how that works. It doesn't matter which ones they are. This will be true for all numbers that have a remainder of 2 when you're targeting divisibility by 3. Okay, so then case 3 would be if all 3 of my numbers were already divisible by 3. Then, of course, their sum would be. And finally, case 4, I want to know if could it be possible to have 2 1s and something different? No, there's nothing else you could put here, because if I put a 0 here, the sum of 2 is not divisible by 3. If I put a 2 here, the sum of 4 is not divisible by 3. So I, in fact, cannot have 2 1s unless I put a third one. The same thing is true of 2 2s. I need a number that's going to add to 6 from 4, and 1 and 0 don't cut it. Or a higher value, but you only have one more number to add, so you're only going to be able to get to 6. It's going to have to be a 2. And 2 zeros, nothing else you can put but 0 on the last one. So then, we know there's none that have 2 of one and 1 of another, so there's only one remaining possibility. That is 1 remainder of each. Okay, so how many ways can I have 3 remainder 1s? Don't forget, there are 4 of each in the pool. Well, we're just going to do 4 choose 3. 4 choose 3 is the same as 4 choose 1. You can think of it as I'm choosing 3 to include in my set, or I'm choosing 1 to not include, right? And so 4 choose 1 will be equal to 4. These are all going to work the same way. You might not know it. I just briefly explain 4 choose 3 and 4 choose 1 are equal. We'll explain why in a different video, but it basically, whenever these two numbers are equal to the top number, then it will be the same. So for example, 5 choose 2 and 5 choose 3. 7 choose 2 and 7 choose 5 are equal. Look up combinations to learn more about that. Okay, so you're going to get 4 of these. There's going to be 4 of these because it's also 4 choose 3, which is 4 choose 1, and 4 of these. How about this one? Well, I've got 4 choices for my remainder 1, 4 choices for my remainder 0, and 4 choices for my remainder 2. And I just get to multiply those. Why? Because of the fundamental counting principle that says we can do that. And so that's going to be 4 times 4 times 4, 64 ways. 12 plus 64 is D, 76. One more problem to go. We'll be right back. All right, so this is the last problem I'm going to cover from the book. If you want to pick up a copy, again, I highly recommend it. I thought it was fantastic. I do feel like it's an upgrade from the mock tests that are available for free. The book is very affordable. He didn't overprice it or anything like that. Just trying to probably cover his costs and then a little bit to operate the business that he runs. So pick it up if you get a chance. Practice Exam 8, Problem 16. We haven't done any geo yet. How can it be AMC level stuff without geo? We've got to do some geometry. Let's get to it. Triangle ABC is isosceles with that true and BC equal to 8. Before we progress, let's make something that looks like that. Maybe we could call this one of the lengths and this one of the lengths and over here the other. So you would have 5 and 5. I don't know if that looks quite, I'm not sure if it looks quite isosceles, but it's going to have to work for now. A, B, and a C. And then this, of course, is 8. And the first thought that you should have with isosceles triangles is that when you drop the altitude, you get 2 congruent right triangles. And immediately when you drop that altitude, probably even as you're dropping it, your brain has already processed that this is a 4. And because that's a 4, the height is 3. Okay, so that's not happenstance. That's by design. Good design, I might add. And so then where are we going to go with this? How are we going to use it? Well, we got to progress in the problem to the rest of it before we figure out how that's going to be applied. But rest assured, it will be part of the problem. Point P is inside triangle ABC such that the product of the areas of APB, APC, and BPC, I'm going to change this to this. So P is like somewhere in here. We don't know where exactly. Such that the product of the areas of APB, APC, and BPC is maximized. We want a maximum amount. What is PB? Well, that's easy. It's peanut butter, I think. Okay, no, it's not actually peanut butter. There was the length of the segment PB, of course, not the common American food for our peanut butter and jelly sandwiches that some of us ate as children. Maybe you didn't. Okay, so how are we going to do this? To be honest, I didn't use the prescribed method. I just kind of use my own technique, and I call it farmer's fence. Where did I get that? Well, in algebra, there's some farmer John or something or another, and he wanted to maximize the area of his fence, but he had a limited amount of perimeter that he could use. So for example, let's say that his perimeter was 36 he could do it with. What is the maximum area that he could make? The maximum area was always a square, right? And so you would say that it's 4 sides of 9. The maximum area is 81. If you went down and said made this 8 and this 10, then you would still have a perimeter of 18, but immediately the area would go down, which is another thing, right? When you have a perfect square and you adjust down 1 and up 1, the area or the value of the product is going to be decreased, okay? So because of that, my first thought was, they're probably all equal areas. I mean, that's just logical that if I'm multiplying three things, I'm going to want them to maximize. Since if one goes up, the others go down, I've got a limited amount of values that I can put in there, then they're probably all going to be equal areas. And I use that to complete the problem. I did want to point out though, I've never really gotten a lot of use out of AMGM. It's raved about in the AOPS forums, and it probably is really great, to be honest. It's my weakness, and so I need to improve myself. Again, how can I do that? Books like this give us the opportunity to be able to make those kinds of improvements, to practice these concepts. So what does AMGM say? It says that the arithmetic mean, that's the AM part, is going to be greater than or equal to the geometric mean of any set of numbers. Okay, that is the AMGM inequality. Okay, so for us, if I was to add up these areas, there's three of them, right? Add them all up, they would have to equal the total area of the whole thing, correct? And if I then divided that by 3 to get the arithmetic mean, which means average, right? Then their average would be 1/3 of the original triangle's area. And since the original triangle's area is 1/2, why did I put 8? I'm thinking of the 8 base, and my brain skipped ahead there. 1/2 times 8 times 3, that's going to equal 12. If I then divide that by 3, the arithmetic mean is 4. This is going to be greater than or equal to the cube root of all of their areas multiplied. I'm just going to call them x, y, and z as their areas. Okay? So why am I doing this with this? Why does it AMGM? How would I know to use this? Well, in the geometric mean, it's cube root because there's 3 things, right? The geometric mean of n things is the nth root of the product of those n things. So what would trigger in our mind that this is applicable? It would be when it asked the product of the areas is maximized. The product, there's 3 things. Multiplying them and trying to maximize that is AMGM inequality. And so you could have recognized it. This is a little bit more highbrow, if you will. It's more impressive. But Farmer Spence works fine for me, but it's probably better to be equipped with these kinds of skills. So the reason why we want them all to be equal is because the only way that this is equal to this is if all 3 of these are 4. Right? Because then you would get the cube root of 64. By necessity, if I lower one to say 3 and make another one 5 and keep the other one 4, you can check that's less than 64. And because it's less than 64, it is not maximized. And that's the goal, to maximize. So just like the Farmer Spence, oh, by the way, one quick note on Farmer Spence, random over there tangent. If you have a river, it's not a perfect square. It's actually going to be x, x, and 2x, the dimension. So if you had 36 again, this would be 9, this would be 18, this is 9. You know, you get the cows fenced in by the river, and for whatever reason they don't go swimming or something, then you could do it with that. Your teacher will not accept that. Even in your calculus class, you're going to have to show it with, various things, other prescribed methods, not just, well, I happen to know that's true. But in math competitions, no one cares about the shortcuts that you take. Isn't that great? Okay, so these are all 4. That's the point. And because they're all 4, we can actually find the area of this. It will be 1/2 times the base of BC times the height needs to equal 4. And then that means the height is 1 because it's 4h equals 4. So this little piece 2p is going to be a height of 1. Now, what does it ask for? PB, it wants to know the hypotenuse of this triangle. And so you're just going to do Pythagorean, get root 17, get D. I hope you enjoyed the video. Check out the book. It's just brand new, so it doesn't have a lot of reviews yet. Give it a look through on there. There'll be some reviews. In fact, Osman Nall gave it a review. Forgot to mention that. He's amazing. So check out the book when you get a chance. I will see you guys later. Feel free to look in the description again for the class sign-up sheet. I will be teaching that class in January. Hope you guys had a great Christmas, and I look forward to growing with you as a channel in the future and looking forward to your success.